Hi everyone, welcome to today's chemistry presentation. In this video, we'll explore one of the fundamental concepts that explains how atoms come together to form molecules. The valence bond theory. What are orbitals? An orbital is defined as a three-dimensional region, aka the spherical region, around the nucleus of an atom where the probability of finding an electron is maximum. The electron is constantly revolving around the nucleus. The electron is either revolving the x direction, z direction, or the y direction. Here are some examples. S orbital or spherical, p orbital or dumbbell, d orbital or double dumbbell. Points of valence bond theory. The first point is covalent bond. Covalent bond is formed by overlapping of atomic orbitals of two atoms. In this example, the hydrogen has one electron facing upwards while the chlorine has one electron facing downwards. So when they combine together to form an overlapping region, this is where the covalent bond forms. The second point is type of orbitals. It teaches that only half-filled orbitals overlap to form a covalent bond. In this first example, both hydrogen and chlorine has half-filled orbitals which forms a covalent bond. While in this second case, the s orbital has two electrons while the p orbital has only one. Covalent bond does not form between them because s orbital is complete having two electrons while the p orbital has only one electron. The third point is spin of electrons. It teaches that the spin must be opposite in the overlapping orbitals. There are three cases. The first case is 2p has one electron facing upwards and 1s has one electron facing downwards. So these both orbitals will overlap together because they are in the opposite spins. In the second case, the spin of the orbitals are neither upwards, they will not overlap because they have the same spin. While in the third case, in this case, our orbitals is completely filled, but we need both orbitals to be half-filled so they will not overlap together.
Greetings, my name is Don Kian Sales, which most of you already know watching this video. So, in this video, me and my partner Mieke Distor is going to explain to you valence bond theory. She already explained what this theory states and some of its points. She ended on the 8th slide here sa spin of electrons. So I'm gonna be taking her spot and be explaining to you the remaining points that are untackled or not yet discussed. So the next point is identity of orbitals. This point teaches us that orbitals retain their original identity even after overlapping. So this means that even after bonding, they will keep their identity. Their identity will not change and will remain the same. For an example, here we have hydrogen and we have chlorine. So you can see one is spherical and one is dumbbell shaped. Even after mixing together, or bonding rather, hydrogen is still spherical and chlorine is still dumbbell shaped. So, moving on to the next point, the number of bonds. It states here that if you have one unpaired electron, you will form one bond. If you have two unpaired electrons, you will form two bonds. If you have three unpaired electrons, you're going to form three bonds, and four unpaired electrons will form four bonds. So it's very simple and easy to understand. If you have this amount of unpaired electrons, you're going to form that amount of bonds. So for an example here, we have nitrogen with 3 unpaired electrons. Now it has 3 bonds bonded with hydrogen. It has 3 bonds because it has 3 unpaired electrons. As simple as that. Next is 6th point, intensity of overlapping. This point teaches us that overlapping between orbitals should take place at optimum or suitable position. So it should not be too much and it should not be too less. It should be at optimum or suitable position. This one, the orbitals are too close to the nucleus, so that's not gonna be suitable or ideal. For this, however, they're not that close to the nucleus and they are just enough to fit or share an electron together. They formed a, what do you call that again? It's a region. It's a region where they share the electron, so they're just making a minimum space for that. They're not doing too much or doing too less. So that's it. Next, the 7th point is bond energy and bond length. This point teaches us that the extent of overlapping decides the bond energy, the bond strength, or the bond length. We can say that the extent of overlapping is directly proportional to the bond energy or bond strength. So, in equation terms, the extent of overlapping is directly proportional to the bond energy or bond strength. If the extent of overlapping is high, then that means the bond strength or bond energy is also high because it's directly proportional. They're gonna stick together and remain the same. I mean, follow each other, because if one is low, the other is also low. So that's it. Here's for an example. This one here, the purple dumbbells are bonded side to side. They have minimum overlapping, which means that they have smaller bond energy, but they have high bond length. Because I stated earlier that the extent of overlapping is directly proportional to the bond energy or bond strength. But what about the bond length? Well, that's taken, or that's already given. If it's not directly proportional, then it is inversely proportional. If there is a minimum overlapping, there is also a smaller bond energy, and there's gonna be a high bond length. For this one, the yellow dumbbell, it has a maximum overlapping, which means it has a high energy but a smaller bond length. That's the relationship between the bond strength or bond energy, the bond length, and the overlapping, extent of overlapping. Next point, sigma and pi bonds. So I'm gonna explain on this point what you just saw here on the previous slide, the purple dumbbell and the yellow dumbbell. So axial overlapping, which is also known as head-to-head overlapping, and parallel overlapping, which is also known as side-to-side overlapping. So if it's the head and the head bonding together, that's called axial overlapping or sigma bond. So this one here, the yellow dumbbell, that is an example of sigma bond or axial overlapping. If that is sigma bond, then this is pi bond. When it's overlapping side to side, just like that, it's just connecting. Pi orbitals overlap like this. It is called parallel overlapping or side to side overlapping. Remember that this type of overlapping will always form pi bond. So if it's overlapped side to side, then that is pi bonds. In basic terms, if they are not really seen touching or actually merging together, that's pi bonds. But if their head touches, then that is sigma bonds. And I would also like to introduce a topic that comes into play a lot with our main topic, valence bond theory. I'm gonna explain hybridization. However, it's not in the PowerPoint presentation because it's not really planned. I just wanted to add it. It's up to you if you want to listen or not, but I would suggest you do because this comes into play a lot with valence bond theory. I don't have any pen right now. Wait. Hello, I'm back. So I'm gonna be explaining here hybridization. I'm gonna show you a very basic concept of bonding first. A bonding so simple that you don't even need hybridization. This hydrogen gas. So when they bond together, they form hydrogen gas. What will it look like in terms of using arrows or spins of electrons? As easy is just gonna look like this. It's bonded together very easily. So now I'm gonna show you a concept or a bonding where you need hybridization. Also, I forgot to show earlier just basic name part where they are in, like the 2p 2s, you guys know that. So here I'm going to show you a different bonding, methane. So methane, this is carbon and this is 4 hydrogen atoms. So my question is, how do you think they will bond together to form methane? If your answer is just to take away this arrow, put it here, take away this arrow, put it here, take away this arrow, put it here, and take away this arrow, put it here. That's how you bond methane. If that's your answer, I'm sorry, but you're wrong. But why? Where did I go wrong?
Where do we go wrong? I know we started out alright.
Remember the part here where you remove this hydrogen atom to put it here, and then this to put it here. Notice that here you formed one electron from carbon, one from carbon, and one from hydrogen. Same here, you filled in this part with one carbon atom and here for one hydrogen atom. Now in this part it's different because you used 2 hydrogen atoms. You didn't even use a carbon atom, so that's wrong. Hybridization, the purpose of it is to bond and create a balance in the bonding process, or the results rather of the bonding, where they should have all equal energy when they bond. This is not equal because they formed a bond of 2 hydrogen atoms, not 1 carbon and 1 hydrogen. So I'm going to teach you now what really should happen. So here, how hybridization works is you combine this 2s here with this. So you're gonna remove this, and instead of 2p, 2s, and 1s, you're gonna form This is the correct one, okay? Here, this box. They're gonna form SP3 with 4 boxes right there. And then one S here. If you're wondering why it turned into SP3, there are 3 kinds of hybridization: SP3, SP2, and SP. This one falls onto SP3, but we're not gonna talk about that more because you came in this video for valence bond theory, not hybridization. I'm just gonna explain the concept because it comes into play a lot with valence bond theory. So, what happens here now is the 2 carbon atoms from or electrons rather. The 2 electrons here are gonna go here. And remember Hund's rule, was it? The one where you have to fill in the empty spaces first. I mean, you have to fill it up first with all upward spins before downward spins. Correct me if I'm wrong, I forgot. But this and then this, because there's 2, right? So there should be 2 here as well. Now there's also 2 here, so that's gonna go here and here, because again, according to Hund's rule, we're gonna first put upward spins in each box or spaces before we're gonna move to the downward spin. Now this is perfect for 4 hydrogen. We have H4 here, right? That means we have 4 hydrogen atoms. And that's perfect because 1 hydrogen atom has 1 electron, which is gonna fit here because we have 4. And each atom has 1. We have 4 empty spaces here. And each 4 empty spaces, or unfilled or incomplete spaces, needs just 1 more. So we're gonna put 1 hydrogen atom here. Now that's gonna turn to H3 because there's only 3, because we took 1 hydrogen atom here, and then here that's gonna turn to 2. Here it's gonna turn into 1. We only have 1 hydrogen now, and once it goes here, it's perfectly balanced. Here you used carbon, that's perfect, that's alright, because it's not an unpaired electron. Remember what I said earlier. So this one, you formed 1 carbon, 1 hydrogen on all 4 boxes. So that is it. That is the concept of hybridization. The valence bond theory ended way earlier. This is just an addition because, again, hybridization comes into play a lot with valence bond theory, and I just want to make sure that if ever no other groups will be able to explain this, I hope I am able to give you a little bit of knowledge so that if ever there's going to be a situation where you're going to need this, at least you have a little bit, just a little bit of information in this concept. So thank you everyone. Good night.